Well, I'll be talking about a technology which we've entitled Femto to Macroscale Interdisciplinary Sensing with a completely novel class of sensors, what we call the tensioned metastable fluid detector sensors. What's the challenge over here? The challenge over here pertains to sensors for nuclear radiation. Nuclear radiation sensors have been developed over the past 80 years, and they're currently being utilized as is. These are the old-fashioned sensors that have been developed for nuclear power and for nuclear explosives, extremely high-intensity fields. But the present-day needs have come down in intensity by about 1 billion times. So the sensors that have been used in the past that are being force-fitted into current-day systems are simply not cutting it, in the sense they're not efficient enough, they're not so inexpensive enough, and they require a fair amount of electronics and complicated machinery to do their job. So the challenge is essentially to come up with transformational sensor systems that are at least 10 to 100 times lower in cost, about 10 to 1,000 times improved in efficiency, and to provide detection of special nuclear materials like uranium and plutonium that could be in warheads in near real time. What are the major innovations that we've basically accomplished to sort of come to this particular goal? The innovations come up in thinking outside the box now. Instead of using old-fashioned methods for charge collection and for scintillation-based systems and semiconductors, we've gone back to basics in the multiphysics approach, thinking about a rubber band being stretched. As you stretch a rubber band, the molecules get weaker and weaker, the interfacial forces, that is, and you can poke a hole inside them. We do the same thing with fluid molecules. Liquid, like water and acetone, the molecules are held together by intermolecular forces. The more you stretch them, the weaker they become, and now you can poke a hole inside them and create tiny bubbles that grow and collapse, and you can see and physically hear the manifestations of a femtoscale particle like a neutron. We've come up with two architectures. One of them is called the centrifugally tensioned metastable fluid detector, that's a CTMFD. Other one is the acoustic-based system. And we've been able to sort of apply them for a vast series of application areas, all the way to combating nuclear terrorism, which is one of the grand challenges of the 21st century, to monitoring for radon in air. Even in a room like this, there's radon that people breathe. It comes out of uranium decay chain, and it causes over 21,000 deaths in the US alone. Why are there not radon sensors in homes? Because they are $10,000 plus. You need to come down to the cost phase of about $100, just like a smoke detector or a carbon monoxide detector. Also used for medicine, for science, energy, and educational areas. And we've come up with a series of rather thought-provoking results. Intrinsic efficiencies of these sensors that you're going to see demonstrated are already about 10 to 1,000 times greater than state-of-the-art. Our costs have come down by a factor of 10 to 100. Our sensitivities are about 100 times better than the best available sensor systems and spectrometers that are available out in the field. And we've also maintained all of this sensitivity for the particles, the nuclear particles that make sense for you to detect, for example, neutrons that come out of special nuclear materials rather than gamma photons that come out of bananas in your body. Yeah? So with that, I would like to introduce the rest of my team over here. There's Alex Hagen. He's my graduate student, and he's going to talk about the centrifugally tensioned metastable fluid detector. Thank you.
As Professor alluded to, a centrifugally tensioned metastable fluid detector is able to detect neutrons and other particles using a negative pressure in fluid. This is an example of a centrifugally tensioned metastable fluid detector. The bulb down here generates high negative pressure, and the elbows are able to self-balance the pressure field inside and keep the fluid in a metastable state. Today I'm going to demo a sensor unit where inside the bulb, the negative pressure will see a neutron come into the bulb and create a cavitation and a vapor column, which are easily detectable by visible light, infrared light, and sound. And I'm going to show you a couple radioactive sources. So the first source I have is a cesium source, which is similar to those used in medical applications. It gives off gamma rays and is pretty innocuous. And you can see that this source is easily detectable by a typical Geiger counter, although it's innocuous. This source here is actually the first approved public neutron demo source. And so this generates neutrons and gammas and has a similar signature to special nuclear material as you might find someone trying to illegally traffic. You can see that the Geiger counter detects it just the same as the innocuous source, giving you no information about whether the source you're detecting is nefarious or innocuous. So you can see when I put the detector over the gamma source, it will not detect. However, when I move it over the neutron and gamma source, it will detect. Thank you.
So today I'll be talking about the application of tension metastable fluid detectors in the field of photonics. Specifically, I'll be showing you a video of an experiment where we can detect a nanosecond pulsed nitrogen UV laser. So in this video, you'll see the detector operating in its nominal sensitive state where it's spitting. Then you'll see a freeze frame showing the laser impinging on the detector sensitive volume. We'll transition to high-speed video showing the manifestation of a bubble vapor column. And it is the presence of these vapor bubbles that actually is the signal that our detector is monitoring. And it is the direction of this vapor bubble column that is forming, which gives directionality information from where the laser is actually coming from. Then you'll see the coalescence of these bubbles into a vapor column and the detector actually registering a detection event.
So one of the other unique opportunities of capabilities of tension metastable fluid detectors is actually the ability to detect alpha detection and alphas as well as neutrons. And so this system is actually a tabletop system that we developed. It's very similar to the portable system that Alex Hagen showed you previously, but we can also do alpha spectroscopy with the system. That allows us to actually develop and monitor the number of actinides that are dissolved inside of a fluid, something that would be very useful for nuclear fuel reprocessing streams. Another common household radon or alpha emitter is actually called radon. Radon's in everyone's house, and as he mentioned, can lead up to about 21,000 deaths per year. So we've developed a system to actually sample the air, and we can look for any airborne radioactive contamination. And this simply just pulls in the air through the fluid. We actually concentrate the alpha emitter inside of the detector fluid itself, and then we can transition that into the CTMFD itself, and then we can monitor for what types of actinides are present, and then at what levels they're present as well too. Another system that we're developing is actually called the acoustically tension metastable fluid detector. So this one is conversely to the centrifugal systems where you're actually spinning the system to stretch and create these tension metastable states. With this system, we're actually using acoustic forces. When driven at the right resonant frequency, you can create a standing wave inside of the detector similar to the way that a laser works. In these tension states, you have this high tension, you're sensitive to nuclear particles, but then you have this high positive pressure state where it actually kind of condenses the bubbles back down again, and then you can become sensitive to those particles again immediately, and you don't have to slow the system down. One of the unique things we can do is when these cavitations happen, you have these large cavitation signal and shock wave. If we look at the timing of these shock waves with PZTs that are attached to the outside of the sensor, we can actually calculate the position and the timing of these events, and then actually tell where these neutron sources are located from. So in this video, we'll actually show you the simulation of the radiation portal monitor, and then you can see the kind of the directionality and the localization of this. So what we'll show you is actually a demo of called a radiation portal monitor. In this case, we're looking at multi-sided pedestrian or a package scanning monitor. So we've set up in an array. This is simulated of 6 detectors in different panels. And then we actually have a moving conveyor belt with irradiation sources smuggled inside of one of these boxes. And then actually looking at the neutron detection rate and the directionality, we can figure out which one of these boxes the radiation source is hiding in. And this is fairly fast moving. So this is moving at 1.2 meters per second.
Over the past 10 years, we've been able to come up with a technology that has essentially revolutionized the way in which we monitor for nuclear materials, as well as for application in medicine, et cetera, including for our own personal health, lung cancer deaths. We talked about radon. There's 1 part in 10 to the 17 in a quadrillion that you're monitoring in virtual real time, something that takes weeks and months sometimes. We've been able to come up with sensors that are 10 to 100 times lower in cost, and as well as efficiency. And Purdue University, together with private investor groups, have now started a company called Sagamore Adams Laboratories that is helping to commercialize this technology. And that's where Brian Archambault is the manager for it. Thank you.